Hello everybody, welcome back to the Altium Academy channel. I'm your host, Zach Peterson. Today, we're going to be talking about the 5 most common myths you will see in DC power integrity. Now, of course, DC power integrity is very important for power electronics because DC-DC converters and similar designs are one of the most common types of designs you'll ever create if you work in power electronics and you're not working at the utility scale. Now, if you buy into these 5 myths, you might make some suboptimal decisions in your design, and that's why I want to discuss them in this video. So let's go ahead and jump in and get started. Now in this video, we're going to discuss the 5 biggest power integrity myths that happen in DC systems. Now later, we're going to do another video about AC power integrity. In this video, I want to really focus on DC power integrity because even it has some challenges that can cause you to make suboptimal decisions in your PCB design. These myths relate to the use of certain industry standards, heavy copper, vias, and of course, component placement in your PCB layout. So without further ado, let's go ahead and jump into myth number 1. The first myth you'll find in DC power integrity is that IPC 2152 and 2221 are the gold standards in thermal analysis. The reality is that they each have limited applicability and sometimes they produce results that contradict each other. Now, why do IPC 2221 and IPC 2152 matter in the context of DC power integrity? Well, both standards contain guidance for sizing traces and rails so that they can carry enough current to limit temperature rise in the PCB below a certain value. These standards were developed with different sets of data and they can produce different values or different trace width requirements for a given temperature rise limit that you impose in your PCB during operation. Now, a little more background on IPC 2221. It is a generic design standard and it contains guidance on all sorts of aspects of PCB design. Things like annular rings for vias, things like trace spacing or copper spacing in high voltage design to meet creepage and clearance requirements, and of course what we're discussing now, trace sizing at high current. IPC 2152 is much more focused on that last issue, sizing traces and rails sufficiently large to limit temperature rise at a certain current value. Now sometimes these two standards actually produce the same result. Here I'm on the Altium blog and you can see here that I've pulled up an IPC 2221 calculator article for PCB trace current and heating. Now in this article, I have placed a calculator for the IPC 2221 trace width, and you can go through here, enter in some values, select the whether a trace or a rail is internal or external, and select some copper weight values, and then you can calculate a result here. So for example, if we bump this up to 2 ounce per square foot copper weight, you can see here what the rail width becomes in that case. So we can go through and play around with these values. And basically this shows you how wide you need to make a power rail in order to handle this 20 amps of current and to limit temperature rise to 40 degrees C. Now here I also have an IPC 2152 calculator on the Altium blog, and if you scroll down here, I've put in basically the same amount of information plus the additional detail that is requested in the IPC 2152 standard. So here you can see where the two standards start to diverge. IPC 2152 clearly takes account of more information in its prediction of the rail size for a given current and temperature rise. You can see here that we have the same copper weight allowances, but it accounts for the PCB thickness, whether or not there's a plane, what is the area of the plane, and then what is the distance from that trace to the plane. And you can see here that if we do this calculation, that we get a similar copper area and rail width as we get with the IPC 2221 standard at the same current and temperature rise. Now, despite the fact that there are cases where these two standards will overlap, the two standards developed their guidance based on totally different methodologies and experiments. And I talked about this issue with Mike Jouppi, who was originally working on the IPC 2152 standard. Let's take a look at a podcast clip with Mike Jouppi.
You know, this is kind of funny because there are certain more experienced designers than myself who are well known, who have said that things like copper planes and copper pour do absolutely nothing for thermal management. And you're saying that they're wrong, and you have the data to prove it.
Big time.
Big time.
Well, copper is 1,000 times more thermally conductive than the dielectric material.
Well, of course. Yeah.
How can it not impact the trace temperature rise?
No matter which standard you choose to use to size your traces and rails for high current interconnects, you should always build a test board and actually do the thermal testing yourself to see if the board is going to sit within the required temperature range. Calculators from standards are useful and thermal simulations are also useful, but unfortunately you have to always do the test yourself, especially when it comes to thermal issues in PCB design. Myth number 2 says that heavy copper is always better in a DC power system. Now don't get me wrong, heavy copper has its uses. The problem is that you can't fix a design that's failing thermally by just adding in heavy copper. There's usually a lot more going on that's causing the thermal failure, and unfortunately you often can't manufacture the exact same design when you take an existing design and bump up the copper weight to try and account for thermal issues. Sometimes instead of bumping up the copper weight, it actually makes more sense to just add more internal layers. That way you can get more copper into the design, but it doesn't really change many of your manufacturability constraints. Let's take a look at what happens to the manufacturability constraints if you take an existing design and bump it up to heavier copper. So here I'm on Advanced PCB's manufacturing capabilities page, and I've shown this page in other videos, and it gives a really good look at what happens to manufacturability when you start to add heavier copper into your inner and outer layers in your PCB. Take a look here at the trace and space section. Here, if we have a base copper thickness with a low copper weight, you can see here that we can get to very small trace widths and clearances. But if we start with a heavier copper, we have much larger required clearances. Same thing happens when we're looking at the trace width and spacing on the outer layers. Here you can see that when we start with a low copper weight, we can have much smaller features, but when we get up to higher copper weight, we're required to have much larger clearances on those outer layers. Now this is important because it goes exactly to the point that I just made about taking an existing design that's failing thermally and trying to solve it by bumping up the copper weight to a higher value. If you have a high density design where the clearances are already really tight, simply going from a 1 ounce copper to a 3 ounce copper could increase your clearances so much that you have to make significant changes to the layout. In that case, it makes a lot more sense to just add layers to the interior of the stack up, especially if you're already starting with a multi-layer board. But what if you have a 2-layer board that has low component density and you don't have a lot of parts and you've already left a lot of clearance in between the parts on the surface layers? Well, in that case, it makes perfect sense to bump up the copper weight to a higher value. If you've already left a lot of clearance margin between the parts, going up to a higher copper weight is going to leave plenty of room for those larger clearance requirements in between the copper features on the surface layers. Now, that's not the only thing you need to do to solve thermal problems in a DC power board, but it can certainly help, and you can get a sense for how much it can help just by looking at some of the rail width predictions from the IPC 2221 and 2152 standards. Myth number 3, every power rail needs its own power layer. Now, I'm not sure where this myth originated, but it is definitely true that you may see a lot of designs that use a power layer and they only dedicate one net to that entire layer. Now, it may appear that this is done because that power layer has to carry high current, but the reality is that this is most often done because someone is looking for convenience of routing. When you have an entire power layer dedicated to a single net, it's very easy to access that power net for your components just by dropping a via and then connecting to the pins on your components. However, in many cases, you'll actually see designs where reasonably high current is placed onto a rail and that rail is shared with other rails on the same power layer. Let's take a look at one of the example designs we've shown on the channel. I have our Ethernet switch project pulled up, and if I go into 2D, you can see here we're looking at the internal power layer. Well, if you take a look at this power layer, you'll see that this layer is actually divided up into multiple rails, some of which are operating at different voltages. So for example, if I just turn on polygon selection and select this net, you'll see here that this is the 1.0 volt net. Here you can see we have another net, which is the 1.8 volt net. So it is perfectly acceptable to divide up your power layer into multiple rails, even if those rails are running at high current. The key is to just make sure that you allow for enough copper so that you don't get an excessively large temperature rise in the interior of the board. That could lead to hot spots, and those hot spots would be visible with a thermal camera. In the case where you do get hot spots and you have a multi-layer board similar to what we have here on screen, you might just need to add another power layer, just like how I discussed in the previous myth. Myth number 4, you can never have too many vias. The reality with using vias to transfer current through multiple layers is that you eventually get diminishing return for those vias. This also holds for thermal vias that are used on die-attached pads in many integrated circuit footprints. In both cases, using too many vias cuts up the internal plane layers and causes them to reduce their current carrying capacity. Let's take a look at an example on screen. Here I have the fabrication data pulled up for a power converter module, and here you can see one of the copper layers is in the foreground. Here you can see we do have a lot of vias in this design, and as I start to turn off the layers, you can start to see where some of those vias start to cut up an internal rail and reduce its current carrying capacity. If I just turn off a couple more layers and focus on this power layer, you can see that the situation gets pretty bad for this small rail on the left. Those vias have basically turned this rail into Swiss cheese. Because this rail has been perforated so much by all of these vias, its current carrying capacity is severely reduced. And the best approach is to try and find the right balance that keeps solid copper between all of those via hits. That way you won't have all of these big open spaces like you see right here, where we won't get any current flow in this rail. Now, if instead of vias carrying current or carrying power, we just had thermal vias on the bottom side of a die-attached pad, we would basically get the exact same result if we put too many of those vias into that die-attached pad. We could get this same type of perforation depending on the size and spacing between those vias. Now, I addressed this issue with thermal vias in another video where we reviewed an article published in iConnect and written by Dr. Johannes Adam and Douglas Brooks. In that article, they found that a surprisingly small number of vias was capable of efficient heat transfer between two pieces of copper, even at high power dissipation. This definitely calls into question the typical guidelines from semiconductor manufacturers to use a large number of thermal vias in the die-attached pads in semiconductor footprints. Now, if you're not sure how many vias you should use, my advice is to at least space them out so that you get solid copper in between those vias and you don't get the big voids like we saw on screen in those Gerber files. The same goes for thermal vias. Make sure you leave enough space between those vias so you don't create big voids in the power rail, and you'll still be able to have highly efficient heat transfer from the semiconductor into the ground plane. And myth number 5, if you have enough copper, placement kind of doesn't matter. The reality is that placement always matters, and in the case of DC power rails running at high current, it actually matters a lot. The reason it matters so much is because copper has finite electrical conductivity, and that means different path lengths along a DC interconnect will have different resistances and thus different power dissipations. This also means that different components in a power circuit could experience different current loads depending on their placement with respect to a load. Let's take a look at an example on screen. Here I have a power regulator circuit with a bridge topology driving current through an inductor, and you can see I have the inductor selected here on screen. In this view, we can trace out the current paths between the high side and the low side FETs on both sides of this inductor. What you see here is that the placement of these two FETs above the inductor causes them to have slightly longer path length through the inductor. And that path length difference can cause each of these legs to have slightly different current when each side of the inductor is being driven. At low current, you probably won't notice a power dissipation difference at different points in the circuit. However, at high current, you might notice a difference, and the result is that one of the components in the circuit might experience an unacceptably high current level. This could cause the component to fail and the circuit to become non-functional. Now, this is something that I discussed with Caleb Buck when he appeared on the Altium On Track podcast. Let's take a look.
We only have one connection point, so same design, one connection point. So then advance to the next slide if you don't mind there. So this is the same load, same source, but the way that it is connected through the board is now causing an imbalance on the components themselves. Scenario 3 puts the source and load on opposing corners of the design. In this case, we still have the high current density areas in the corners just because we're turning a corner with that high current. But the path distance from the source to the load averages out to be approximately the same for each parallel path so you actually get reasonable distribution of the current across the devices in this scenario.
The takeaway here is that placement and routing around a load may need to be symmetric in order to ensure you get even power dissipation around a power circuit. This can be checked with a DC power integrity simulation, and that will show you the current distribution in your copper rails in your PCB layout. Now, we have a video showing how you can do this using the Keysight Power Analyzer extension inside Altium Designer, so make sure to check out that related video. Link is in the video description. Thanks for watching this video, everybody. Make sure to check out the resources in the video description. And as always, leave your comments and questions in the comment section. And last but not least, don't forget to call your fabricator, folks. We'll see you next time.